la doctora Analía Longinotti y la codirección de los doctores Jair Herrera y Daniel Rosa. El jurado de este examen está conformado por los doctores Barram Chavallucia, Raúl Mujica, Alfredo Montaña, Takamitsu y la doctora Irene Cruz González. Sin más, vamos a dar comienzo a tu presentación, Mauricio. Tienes de 30 a 45 minutos exactamente, no más, y pues adelante.
Bueno, primero que todo, muchas gracias por venir. En esta ocasión la plática la voy a dar en inglés para la solicitud de unos ciudadanos. So, thank you so much for having me here. Today I'm going to present my thesis work, and you already heard about the title on the supervisors. This thesis was supervised by Dr. Analia Longinotti from UNAM, Dr. Jair Herrera from UNAM, and Dr. Daniel Rosa González from INAUA. So, I'm going to start. First, I'm going to talk about the general view of the talk, and first I'm going to introduce about the active galactic nuclei, then I'm going to talk about X-ray surveys, the XMN Newton satellite, then I'm going to present our motivation and the principal objective, then the methodology with all of the steps that we need to accomplish of principal objective, for example, the X-ray data reduction and source detection. Then I'm going to present our results, a summary discussion, and the main conclusions. Then the future work after the thesis. Well, first, what is an active galactic nuclei or AGN? So AGN are those galaxies that contain a compact and dense region which harbor a supermassive black hole, which is powered by an accretion disk. From this nuclear region, there are released a really huge amount of energy, reaching, for example, high luminosities, higher than 10 to 42 ergs per second in the X-ray band. Additionally, the range of their supermassive black hole mass is from 10 to 5 to 10 to 10 solar masses. The volumetric luminosity is from 10 to 41 to 10 to 48 ergs per second. And another important property is their intrinsic variability from X-ray with Chandra, with radio with BRA, and optical with MPG. And the combination of those observations we have in the middle. Okay, this spectral energy distribution I showed you in the left, the typical Taiwan AGN set, and on the right, the schematic representation of the AGN physical model. Here, we can observe in the middle a supermassive black hole which is surrounded by an accretion disk, and above of them we have a hot corona composed of relativistic electrons. Then we have the Broadland region and the Atlantic Taras. Further, we can see the polar dust and the Narrowland region. On the left, here we can observe the different components of the AGNs with the dotted lines, their emission, and the integration of all of those components, we obtain the final AGN set. And we can observe that the emission can be observed from the radio to even X-ray or gamma rays. Okay, now, what is the main physical mechanisms for the X-ray emission? So first, I'm going to classify the X-ray emission into two bands. First, the X-ray, the hard X-ray from 2 to 200 kiloelectronvolts, which are produced by the Compton inverse scattering of the optical and ultraviolet sheets from the disk, which interact with the hot corona. Those relativistic electrons from the corona reach temperatures of 10 to 6 to 10 to 8 Kelvin. Then we have the soft X-ray, which is from 0.1 to 2 kiloelectronvolts, and are produced basically by the tail of this Compton inverse scattering. Here we can observe this once again this AGN model where the seed photon is scattering by the hot corona, generating the final X-ray spectrum. Okay. Typically, the classification of the sources into type 1 and type 2 is made with the optical spectrum. For example, here we can see two spectrum of an AGN type 1 above and below at type 2. The classification is with the speed or the width of the emission lines. For example, type 1 have a speed of 100 to 500 kilometers per second, while type 2 have a speed of 500 kilometers typical. And this is associated with the line of view of the observer. For example, if we are observing the torus, we are going to have type 2 AGN. While if we are observing the broadband region or the disaggregation, we're going to have a type 1 AGN. So this is in optical. But how is in X-ray? Okay, this is in X-ray. First, I show you the theoretical AGN X-ray spectrum at different column density, hydrogen column densities, NH, and we can observe how is this spectrum. For example, if we don't have this column density or absorption, we are going to have a power law. Here, we can observe this power law. But if we start to increment the column density, the oscillation is going to start to absorbing the soft band. We can observe how this, as a function of the column density, this hydrogen column density, we can start producing this soft emission. So there is a parameter that we can use to classify those sources into obscure or obscure sources. And this parameter is named the hardness ratio, which have this expression. It's basically the ratio between the hard band tones minus the soft band tones above the sum of both. Here you can see if we have, for example, a positive hardness ratio, that means that the hard band have a more contribution than the soft. So we are going to have an obscure source. And in contrast, if we have a minus hardness ratio, we are going to have a more contribution of the soft band, and then we are going to have a type 1 or obscure AGN. Here, typically, the hardness ratio is from minus to 0.2 for type 1, which corresponds to 10 to 22 centimeters square of atoms of hydrogen. And for type 2, we have a hardness ratio higher to minus 0.2, and a typical column density higher to 10 to 22. Okay, now, what are the main properties of X-ray surveys to detect AGNs? Here, I'm going to list all of those properties. First, we have, since the X-ray signature reveals accretion process, it is a really good and reliable method for AGN identification surveys. Second, since the X-ray emission can penetrate to high column density, as I already mentioned, this emission have a reduced absorption bias. In contrast, we have, for example, optical bands, we are going to have some absorption and we are going to lose information. Then, the X-ray emission of the AGN super low dilution by the host galaxy. And this is really important because if, for example, we observe in the optical or infrared bands, we are going to have a bias for the dust or the starlight of the host galaxy. And finally, the X-ray spectrum of AGN can be used as diagnostic tools of accretion activity. For example, we have the universal power law observed in X-ray in all AGN can be well explained with the two-phase model that I already mentioned, which is composed by the black hole plus the accretion disk and a hot corona with an inverse component scattering. So with this spectrum, we can estimate physical parameters. For example, the luminosity, column density, mass of the black hole, etc. Okay, now an example of this of a deep and a shallow X-ray survey. First, I show you a deep narrow X-ray survey is an observation that distributes the total exposure time over a small area. The main characteristic is that we can observe, for example, moderately luminous AGNs, or we can detect faint high redshift sources. And in contrast, we have the shallow large X-ray survey, which are observations that distribute the total exposure time over large areas. And the properties is we can identify high luminous quasi-stellar objects or quasars or atypical sources. for example, ultraluminous X-ray. I have to mention that both surveys I complement each other. And when we have advantage with one side, we have the disadvantage with the other side. So an example of both, here I show you the XMN Newton change field source for Renani, and in the swallow we have the XMN Newton XXL survey. Here, in the first, Renani observed a 0.25 degrees square, while here observed 25 degrees square. Renani have an exposure time of 3.45 millions of seconds, while here have 6.9 millions of seconds, but distributed in 542 observations. That makes a typical exposure time in average of 10 kiloseconds for each field. So we run out, for example, a really deep observation of 6.6 times 10 to minus 16, while here obtain a really low sensitivity of 2 times 10 to minus 14. And randomly observed 339, while here observed 2000, but in average 120 in the same field of Renani. Okay, this is the difference of both. Now I show you the XMN Newton properties. We use the data and we are working with X-ray, so it's important to mention. First, the X-ray multimirror mission Newton, or XMN Newton, was launched in 1999. They have an energy range of 0.2 to 12 kilowatt and field of view of 30 times 30 arcminutes. It has a spectral resolution of 2250 and angular resolution with a PSF of 6 seconds with 4 we have maximum. We were working with their cameras, with the 3 EPIC camera, is 2 CCD MOS cameras and 1 CCD PMA camera. Okay, now about the survey. So our survey is composed by routine observation made along of 2 years by the X-ray XMN Newton Observatory. This survey was in a field of 30 by 30 arcminutes, and we reached a total exposure time of 1.75 million of seconds. The optical follow-up, we have an optical follow-up in this field with the GTC, with the UGRI and C bands. And additionally, I am the PI of 2 long-slit spectroscopic observations in this field. And we have access to infrared public catalog of bodies and humans. Here I show you a table with the observation, the day, and the nominal and total exposure time. Now, what is the motivation of this thesis? So, as I already told you, the X-ray surveys combined with multi-wavelength analysis are offered the best tools to detect and characterize large samples of AGNs. So, and they hold galaxies at different redshift ranges. Therefore, we can use this method to understand these large samples of AGN, to understand the supermassive black hole process evolution and their connection with galaxy formation. Basically, through cosmological senses of AGN. And the principal objective of our thesis was to analyze and characterize one of the deepest X-ray fields observed by XMN Newton to identify and study all of the AGN population detected in this field. Okay, now I start with the methodology. First, we have the X-ray data reduction and source detection. For this process, we use the Science Analysis System, SAS. It's a software developed to XMN Newton. Basically, it's a collection of tasks and libraries to work with the observation of XMN. And especially, we use the e-detect stack, which is a task prepared to analyze overlapping observation of XMN Newton. But how was this X-ray data reduction? So, it was in this way. First, we clean each observation for high background periods. Then, the task overlaps all of those observations using a common coordinate system. Then, the task estimates the exposure mark for each instrument. Then, it uses this exposure mark to create a detection mask for each energy band and instrument, and basically mark the region where later we're going to do the source detection. And then use the exposure and detection map to estimate the background map.
which perform a source detection window of 5 pixels and then mask dispersion and direct uses for the button map. With the combination of these three maps, the task creates the final stacked images, where we're going to detect those resources. Here, we observe the field of XML Newton. We have in the middle the plaza, and all of those points are the resources, and this straight line is the out-of-plane events, which are basically the photons that the observatory recover when it is not working, and they put all of those photons in this region. Now, this is our result. First, we obtain a preliminary list of 188 resources divided into a point line with 434 and extended with 49. Then we remove 133 point line objects because we observe with the Noise camera and instrumental features, and we delete 34 sources. Then I perform a visual inspection in each observation, and I detect stray lights and hot pixels. Then I remove 29 sources. The final list that we were working in this test was the 321 X-ray point sources. All of them detected with a sigma of significance. Here in the map, in this one, we can observe how we avoid the central plaza and this outline event during our source rotation. Now, at the flux distribution, what was our results? We obtained a soft flux limit of 4203 to times 10 to minus 16. In the hard band, we obtained a 1.3 to 10 to minus 16, and in the full band, we obtained 9.8 times 10 to minus 16 ergs per second per centimeter squared. That made this survey one of the deepest surveys performed with XML Newton, or the most sensitive. We cannot compare these results with the literature or previous surveys. For example, here I show you in the left the soft band is in the right the hard band. And we can observe with the blue dots the Shanda survey, with green we have XML survey, and in red other X-ray surveys. And our results are presented with the black star marked into this square. Here we observe that our results make this survey the third most sensitive XML Newton survey today, and only surpassed by the Renali survey with a little bit more sensitive, but the double photo time and the Lachman survey in a good region with low column density of Doctoral. Now, our results for obscure and unobscure sources. We obtain a total of 70% of unobscure sources and a 30% of obscure sources using the hardness version. And the mean of this value is minus 0.31. Then we perform a log-n Lorentz analysis, which basically is the number of sources per flux limit. And we compare our results with previous XML Newton and Shanda surveys in a small, a large, and medium areas. Here we can observe in the top and in the right hand that in both cases we will see a good coincidence, good results compared with previous surveys. Now, the optical and infrared coverage. So, as I already mentioned, this field has, we perform an optical observation with GTC. In total, it was 16 GTC observations with 1 minute of spatial search. I apologize for these small problems. I'm going to continue with the presentation. So I was talking about the optical coverage. Now I will just summarize the infrared public repositories search for WISE data. So we obtain with a 20 ready search. This is the green circle, a total of 6,000 WISE sources. And additionally, we obtain a 900 human sources. So now we continue with the cross-correlation analysis. So for this cross-correlation, we use the likelihood ratio technique, which basically is the ratio of two probability densities defined with the angular distance and the
optical and infrared or X-ray positional errors. So as a result, we obtain a total of 244 X-ray sources which possess optical and infrared counterparts. Here I show you this histogram with the angle separation for the sources obtained with white in the green and with UTC in the purple. And here are the images with XMM Newton full band in the R band with UTC and white with the W1 band. Now we estimate the photometric redshift. For this estimation, we are going to use the optical bands of GTC. So we use the software Photoraptor, which is a supervised neural network which use these optical bands to estimate this photometric redshift. So first we need to train this neural network. To train it, we use a spectroscopic catalog composed of 824 sources, which are made from our own GTC observation and analysis from a public catalog of Johnson from the same field and the same public sources from Sloan Digital Essay Survey. I have to mention that from these 824 sources, we have 39 X-ray sources of our X-ray catalog. So, how was the training and the test? We use the typical rule of the 80-20, which means 80% of the sources are used to train the neural network and 20% of them are used to test them. And we use as a the input neurons, the optical bands, U, G, R, I, and Z. And we made 20 runs to train it here to take the best conversion of this training network. So our results, here is the training, until to obtain a convergence. So our results was we use the normal median absolute deviation to compute or estimate the reliability of our results, and we obtained a 0.07 of deviation and outliers of 8.5%. Here I show you our distribution of the spectroscopic and the photometric redshift, and the outliers are the red points. And if we remove those outliers, our sigma it doesn't improve too much. That means that it doesn't matter, the outlier doesn't affect our results to estimate the photometric redshift. So this is our results. We obtained a total of 211 sources with redshift, 39 with the spectroscopic and 172 with photometric. And you can observe an upper density at 0.43 in this region. And the largest redshift was obtained with the spectroscopic up to 2.66. The red are the spectroscopic and the blue photometric, and the white is the combination of both. Now, we start with the AGN selection criteria. To select or to identify two sources, we use the combination of the optical, infrared, and X-ray emission. So first, we use this criteria, use it for high luminous AGNs, which is selected for those sources with 3 times 10 to 32 agents per second. Then, for those sources that are not so luminous, for low luminous sources, we use the ratio between the X-ray and the radio band and the air band with the GTC, and the X-ray with the KS band from WISE. And finally, we use the X-ray variability criterion because we're selecting two sources that are statistically variable. So, how was the selection? First, I show you the second and third criteria. We can observe here in the envelope the X-ray, and in the y-axis the infrared, and in the north pole we can observe the X-ray and the air band. Here there is like a gray region that we can observe now, but this is the AGN selection region. In this part we observe 147 AGNs in the second criteria, and the third criteria we identify 117 AGNs. Here is the first AGN criteria. Here we have another, once again, this regression. This is the AGN selector regression, and we identify a total of 173 AGNs. And then we use the X-ray variability criterion. To do this, we use the chi-square statistical parameter to measure basically the statistical that represent the X-ray variability of the source, which use the number of observations, the flux per observation, and the flux error, and the mean of the flux. Then we quantify this variability, this statistical variability using the index, which is basically the minus logarithm of minus, or 1 minus the Poissonian probability of the chi-square. And using a 95% of confidence, we have a B index higher or equal to 1.3. Here I show you the line curves of the source XIT2, and we can see how in the first observation as a really lower flux, then it increased to higher fluxes. And the observation with GTC, with the XMM Newton, we have the images. I had to mention that because it was observation in different epochs, it was time that the telescope missed the source. So we have not all of the observations for each one, but this is important to estimate this variability. Now, what was our results? Here we obtained a total of 71 AGNs with this B index parameter higher to 1.3. We can observe the distribution on the left and the B index versus the convex on the right. So, as summary, we obtained 173, 147, 117, and 21 AGNs detected with the first, second, third, and fourth criterion. And combining these four criterion, we detect a total of 55 active galactic nuclei that satisfy at least one criterion. For example, we use a test sample, and we can observe that in some cases this criteria is accepted, and in other cases this criteria is rejected. This shows you how important it is to use multi-wavelength analysis with the X-ray, because if we use only the X-ray luminosity, we have rejected one source. But if we use the infrared and optical combining with the X-ray, we will accept it. That makes a really more reliable technique to identify AGNs. Here I showed you only a Venn diagram that presents how is combining each criterion with each other. And as a result, I show you 225 AGNs, but from those sources there are only 25 AGNs that satisfy the four criteria. But at least one satisfies the 225, at least one satisfies at least one criteria. Now the X-ray luminosity classification. So we use the X-ray luminosity to identify sources classified as a quasar with luminosity higher to 10 to 44, a Cipher with luminosity in the range of 10 to 42 to 10 to 44 ergs per second, and low luminous AGNs 10 to 42. And those sources with no luminosity X-ray, they were not classified. So all of those sources satisfy at least one AGN criterion. If they satisfy this criterion, according with their luminosity, we obtain a total of 41 quasars, 140 Ciphers, 7 low luminous AGNs, and 37 unclassified. And then for two sources that did not satisfy one criteria, according with their luminosity, we select as a normal galaxies with the luminosity range from 10 to 38 to 10 to 42, and a Cipher candidate for those sources that didn't satisfy one criteria, but with high luminosity from 2 to 42 to 3 to 42 ergs per second. Then we use an optical classification with the absolute G band magnitude. So basically, the sources that satisfy this equation with minus with the absolute magnitude lower than minus 22.3 are selected as a quasar, quasi-stellar object. And for those sources with absolute magnitude higher or equal than minus 22.3 are classified as a Cipher, and unclassified for sources with this G-band or no luminosity. Here I present the distribution. We can observe this trend of our 18 sources. Then we have the green point with the galaxies, and this purple point with the normal, with the Cipher candidates. Okay. Now we have this sample of agents, but we additionally want to study what is the general variability distribution of sources. So we use the next parameter, the normal excess variance, which measure the X-ray fluid's amplitude variation of each X-ray observation weighted by its statistical error. So we have the excess variance, and here are the error. Both are defined as with the number of observation, the fluids per observation, and the fluids error. So additionally, we classify those sources as an upper limit when the statistical error is higher than the excess variance. And we define this upper limit as the sum of both. To utilize those sources to incorporate the upper limit in our analysis, we use a Monte Carlo simulation, which basically it simulates values of the excess variance and the upper limit. Here, the red points are the variance, the blue points the upper limit, and these dotted points are distributed with the errors. So we make a regression line fit for each simulated data. So with those results, we start to analyzing this X-ray variability compared with other physical parameters. First, we have the X variance versus the X-ray count. Here we observe a strong anti-correlation. Here with the black line is the mean fit of all of the data. The red line are for only the variance, the red points, and this dotted purple line are for those sources which are intrinsically variable, with a beta index higher than 1.3. So we obtain this strong anti-correlation, but we propose that this anti-correlation is due for a possible selection effect, which is causing here, there is like a yellow region here. We can observe all of these blue points are for those sources with really low X-ray counts. Yeah, this is populated by upper limits, which weight the distribution. While we have more X-ray counts, we have this good detection with the excess variance, so we can observe this to distribution. So it's imply a possible selection effect. Then we compare the excess variance versus the X-ray luminosity. So once again, here I show the distribution of the X-ray variance as a function of the luminosity, and we obtain a weak anti-correlation, which can observe with high luminosity X-ray sources present low variability in this part. And the low luminous X-ray sources present high variability in this direction. And we use the same dots and marks than the previous plot. Then we make an X-ray spectral analysis of the brightest sources in our catalog. Those sources with 500 counts in average per observation. So what we did, it was as follows. First, we combine all of the spectral data of the three EPIC cameras, PM, MOS1, and MOS2. Then we sum all of these spectra in all of the observation. And finally, we obtain this average spectrum with the black dots. Then we use a spectral model. Actually, we use three spectral models. First, with the galaxy absorption and a simple power law. Then we include an intrinsic absorption of the host galaxy, and finally a third model that includes additionally an X-ray emission of the iron line at 6.4 kilovolts, which comes from a fluorescence effect of the neutral iron. So then we estimate the physical parameter, the fluid index, the column density, and the equivalent width of this iron line emission, the X-ray fluids, and the luminosity. And we estimate all of those parameters with an 80% of confidence. Here I show you these confidence contours with the distribution with the photon index and column density. Each region represents first 1 sigma of confidence, the second region 2 sigma, and the third region at 3 sigma of confidence. Then we analyze the reliability of our results with two statistical tests. First, the F test, and then the AIC test, which both are used to compare the model with one parameter and another model with an additional parameter. How improve according with the parameters that we are using. So these are our results. First, I show you the equivalent width versus the X-ray luminosity. Here we obtain this with anti-correlation, and we compare with previous X-ray surveys. For example, Bianchi 2017 with this yellow dot line, and Ricci 2014. And both obtained the same or similar results than ours. And this distribution is already noted as the Iwasawa-Taniguchi effect, which is explained with the decreasing of the open angle of the torus as a function of the luminosity, or even the iron-emitting material is ionized in the same form as a function of the luminosity. That this with anticorrelation. Then we compare the X-ray variance versus the supermassive black hole. So here I show you this distribution, and again we compare with Lanzuzi 2014 with this yellow line. Well, it's more a green line here that is almost invisible. But we obtain a weak anticorrelation, and we estimate the black hole masses in 2 steps. First, we use this luminosity relation with the luminosity at 5,100 Armstrong, and then we use this mass equation from Peterson. Here we can observe that at high massive sources, we have low variability, and low massive black holes, we have high variability. So that is an important question. We can observe this weak anticorrelation, but we observe a similar correlation with the variability and the luminosity. But here's something interesting, that both present the same slot. So we thought that could be correlated. Then we thought, is the X-ray luminosity variability anticorrelation a consequence of an intrinsic massive black hole variability relation? So according with this slot, and they possess the same weak anticorrelation, we thought in the next scenario to explain it. First, we have to I have to define the viscosity time. This viscous time is the time that the gas particle will be drifted into the black hole. So this time is as a function of the black hole. Then the accretion luminosity, again, is a function of the black hole mass. So it means that if we have a low massive black hole, we are going to have a low luminosity source, which will present a small time viscosity time. And then we are going to have a high accretion rate fluctuation that will obtain a high variability in this process. And vice versa, if we have a high mass black hole, we are going to have a high luminosity accretion rate, and we are going to have a high time viscosity time. And then we are going to have a low accretion rate fluctuation, and then we are going to have a low variability, which is what we obtain. Here we can observe this the luminosity X-ray, and here the X-ray variance with the same distribution as already explained. Okay, that was our main results of the thesis. So a summary of all of them. First, I have to mention that this is the pure sensitive X-ray survey performed by SMM Newton, and the number one center array source. We obtain a flux limited of 4.3 to 10 to minus 16 in ergs per second per centimeter square in the soft band. Then, in our X-ray catalog, we obtain a total of 300 watt point X-ray sources with this sigma of confidence, and our results from the log-n log-s analysis is in concordance with previous SMM Newton and Chandra surveys. Additionally, we obtain that 30% of our sources are obscured and 70% are unobscured, with a mean hardness ratio of minus 0.33. Then we obtain that 244 or 80% of our catalog present optical or infrared counterparts. And from our total X-ray catalog, we obtain a 70% of sources with redshift estimation, with photometric 39, 172, and spectroscopic 39, with the highest redshift 2.66 and an over density of 0.43. Then we obtain a total of 225 new AGNs detected based in this multi-wavelength criteria, with a luminosity range from 1 to 21 to 10 to 41 to 2 to 06 times 10 to 46, and a luminosity, a massive black hole mean of 7.4. Then, from the Iwasawa-Taniguchi effect, we obtain a flat slot with anticorrelation, An explanation of this anticorrelation is presented with the decreasing of the opening angle of the torus as a function of the luminosity, and the same, the iron emitting material is ionizing with this luminosity. And then we obtain this anticorrelation with its variance and the X-ray luminosity and its variance and the massive black hole. So this luminosity variability anticorrelation could be generated as a byproduct of an intrinsic black hole mass variability relation. So what are the future work that we can proceed after this thesis? So first, we can continue with the search of high redshift AGNs. So we can perform an spectroscopy survey campaign around those 22 AGN sources with no redshift estimation. And there could be likely a really high redshift, possible up to 6. Then we have actually proposals with the GTC. I am the PI of those observed proposals. So currently I am analyzing 15 of those high redshift candidates. So then we are going to perform a compounding AGNs detection or identification. For those, we are going to perform X-ray spectral analysis combined with infrared and radio emission to identify those highly obscure AGNs. And finally, we can perform an X-ray binary search. So we already select those AGNs, and there are sources that are not classified. So we thought that we can search for those sources that could be X-ray binary systems or any X-ray source generated by an stellar emission. For example, we have the X-ray spectrum of XID22. It's really associated, or it's really similar to a binary system spectrum, and we have the optical spectrum as well for GTC, which is compared with an star, M class star. And we have the Gaia observation for this source, which is estimated at 222 light years of distance. So, additionally, as I already mentioned, we need this radio emission for the of resources and others. So we already proposed an observational campaign with Toltec to observe this region. So we propose 5 resolution mode observation to cover the full XML Newton field. We expect to have a 0.13 millijansky as a sensitive. And we expect to obtain a signal to noise of 20 in the detection of our resources. So these are the publications presented along of the thesis. Here are the proposed observation campaigns and the Congress symposium and school that I was doing the thesis and the doctoral thesis. These are the reference, and that's it. Thank you so much.
Voy a hablar un poco más fuerte para que me escuchen. Vamos a dar lectura al acta de examen. En el Instituto Nacional de Astrofísica, Óptica y Electrónica, el día 14 de noviembre de 2022, se reunieron los profesores doctora Analía, el doctor Jair Herrera, el doctor Daniel Rosa, el doctor Barán, el doctor Raúl Mujica, el doctor Alfredo Montaña, el doctor Takamitsu y la doctora Irene Cruz, para integrar el jurado de examen final de doctorado en ciencias en la especialidad de astrofísica del maestro en ciencias Mauricio Elías Chávez. Después de examinarlo, resolvieron aprobarlo. Muchas felicidades.
Bueno, muchas gracias a todos por asistir a esta presentación. Fue muy larga y a veces no se me entendía, pero gracias. No se vayan, tenemos aunque son unas copas de sidra y de jugo para los que no tomen, y nos acompañen a un pequeño brindis. Sí. Muchas gracias, doctores, por habernos acompañado. Doctora Irene, Barán, doctor Takamitsu, muchas gracias.
¿No vas a brindar con nosotros, Barán? Bueno, que si no ibas a brindar con nosotros.
Dios, muchas gracias por haber asistido.
Gracias.
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 Ya no.
Chao. Felicidades, Mauricio.
Muchas gracias.